Good afternoon, friends. Let us today's our topic is eigenvalue and eigenvectors, in which earlier we have discussed the eigenvalue and eigenvector, how to find them, then diagonalization process via similarity transformations. Now next we want to discuss the orthogonal diagonalization. So our main concerns are what do we mean by orthogonal diagonalization, that is how to diagonalize a matrix via orthogonal transformations, and then as an application we want to discuss the application to the quadratic form, that is to reduce quadratic form to its canonical form. So let us discuss the main problem, orthogonal diagonalization. So earlier we have just seen the simple diagonalization, in which we find out the diagonal matrix similar to the given matrix A via similarity transformations. So here the problem is, so before going proceeding ahead, let us just revise two simple definitions: symmetric matrix and orthogonal matrix, because later on in the discussion we will be using these two matrices. So a matrix A, square matrix, throughout the discussion the matrices will be square matrices. So a matrix A is symmetric if A is same as its transpose. Transposition means the interchange of columns and rows. So A and A transpose are same, then such a matrix is called symmetric matrix. Then the second definition is orthogonal matrix. A square matrix A is said to be an orthogonal matrix if the product A into A transpose is identity matrix, as well as A transpose into A is also identity matrix. That is, in other words, the transpose of the matrix is nothing but the inverse of the matrix. So one thing is sure from the definition of orthogonal matrix, that orthogonal matrix is always invertible matrix, and inverse of such matrix is the transpose of the matrix itself. Now let us define the problem. The problem of diagonalization, that is orthogonal diagonalization problem. Given an n by n matrix, we seek for the orthogonal matrix P such that the P transpose AP, here the P transpose is same as P inverse, so here we take P transpose AP is a diagonal matrix. So is it possible for matrices? If so, then such a matrix is called orthogonally diagonalizable matrix. And the next question is, for all are all the matrices orthogonally diagonalizable? So all these questions we will be discussing one by one. So let us first define the orthogonal diagonalization. A matrix A is said to be orthogonally diagonalizable if there exists an orthogonal matrix P such that P transpose AP is diagonal matrix. And this transformation P transpose AP, we call it the orthogonal transformations. So, and here the matrix P is said to orthogonally diagonalize A. So here we have two questions to consider. The first one is, which matrices are orthogonally diagonalizable? All the matrices or some of the matrices? If not, then what kind of matrices are orthogonally diagonalizable? And the second question is, how do we find an orthogonal matrix to carry out the diagonalization? So in order to answer the first question, let us see some facts. The facts is about symmetric matrices. So let us discuss the symmetric matrix. A matrix is real symmetric matrix. Here all the matrices are real matrices. So a matrix is symmetric, then one thing is for sure, that all the eigenvalues are real numbers. Then second property of symmetric matrix is that for each eigenvalue lambda, the algebraic multiplicity and the geometric multiplicity is same. And the third property of symmetric matrix is it has the full set of eigenvectors, that is, it has total n eigenvectors, linearly independent eigenvectors here. And in fact, later on we will see that we can find the set of orthonormal eigenvectors, orthonormal basis for eigenvalues. So, and the one more important fact is eigenvectors corresponding to distinct eigenvalues are orthogonal. So let us revise again. The eigenvalues are real, then we have full set of eigenvectors, and the third most important property is eigenvectors corresponding to distinct eigenvalues are orthogonal. So these three things will help us to answer our first question. Now suppose that the diagonalization is possible and there exists a matrix P, orthogonal matrix P, such that P transpose AP is equal to the diagonal matrix. Therefore matrix A is equal to PDP transpose, because here in D is same as D transpose, so multiplying both sides P, we get AP is equal to PD, and then multiplying both sides on the right hand side P inverse, we get A is equal to PD P transpose. Now taking transpose both sides, A transpose is same as, you will verify that we can verify that A transpose is equal to A. So what does this discussion says? The discussion says that if orthogonal diagonalization is possible, the only possible for symmetric matrices, and the matrix is symmetric, then as by the results that the eigenvectors, we have full set of eigenvectors, so that we can get the orthonormal eigenvectors and form the matrix, and we can carry out the diagonalization orthogonally. So we have this important result, that is called spectral theorem for symmetric matrices. This theorem says that if A is an n by n symmetric matrix, then the following three statements are equivalent. That means for any symmetric matrix, it has it is orthogonally diagonalizable, and it has an orthonormal set of n eigenvectors. So total this theorem is crucial for the orthogonal diagonalization. Why? Because in this theorem says that the matrix is symmetric if and only if it is orthogonally diagonalizable. So the only matrices which are diagonalizable orthogonally are symmetric matrices, and if the matrix is symmetric, then you can orthogonally diagonalize. And also if your matrix is symmetric, then the third statement says that the matrix has orthonormal set of n eigenvectors. Also one more fact, the property of the matrix, that is a matrix has all the columns are orthonormal, then such a matrix is orthogonal matrix. So we would get the orthogonal matrix and we can diagonalize the matrix. So by preceding theorems, in view of the spectral theorem, let us define the procedure for orthogonal diagonalization. As we have seen, this orthogonal diagonalization is only possible for symmetric matrices. Therefore let us take an n by n symmetric matrix. At the first stage, we will find out the eigenvalues and basis for each eigenspecies. After finding the basis for eigenspecies, as we know, the eigenvectors corresponding to distinct eigenvalues are orthonormal or orthogonal, but we apply the Gram-Smidth process to each of these bases to obtain an orthonormal basis for each eigenspace. That is, after finding the eigenspaces, we will orthonormalize them and find the orthogonal basis, orthonormal basis for the matrix E, that is Rn. So from the matrix, we form the matrix P whose columns are these orthonormal eigenvectors which have been obtained via Gram-Smidth orthogonalization process of the eigenvectors. And now the product P transpose AP will be the diagonal matrix, same diagonal matrix as the eigenvalues are on the main diagonal. So the procedure says that find out the eigenvalues and eigenvectors. After finding the eigenvectors, apply the Gram-Smidth process to orthonormalize them, and we find out the orthonormal basis of Rn. That is, we get the n orthonormal eigenvectors. Using these n orthonormal vectors, we form a matrix P, and then the product P transpose AP will be the diagonal matrix. So let us make some remark. In this case, the observation is, if your eigenvalues are distinct, all the eigenvalues are distinct, then simply we need to normalize the eigenvectors, and then these normalized vectors are mutually orthonormal, and hence we form the matrix, model matrix P. So in the case where eigenvalues are distinct, it is easy, but when eigenvectors values are repeated, so in the case of repeated eigenvalue, for the repeated eigenvalue we find out the basis for eigenspace. For the repeated eigenvalue we will find out the basis for eigenspace, and here the dimension of the basis, that is, we will get, if your eigenvalue is repeated 2 times, then we will get exactly 2 members in the basis. So we apply Gram-Smidth process to produce the orthonormal eigenvectors from the linearly independent eigenvectors. And after applying the Gram-Smidth process, when you get the orthonormal basis, we find out the we form a matrix P, and hence we diagonalize orthogonally a matrix A. So the decomposition of A into P D P transpose is called the spectral decomposition of A. This is one of the definition. That is why we call it spectral decomposition, because in this decomposition the matrix A is decomposed into the spectrum. What is spectrum? Spectra is a set of all eigenvalues. So the matrix D contains all the eigenvalues in the diagonal. So this matrix is decomposed into using diagonal eigenvalues. Therefore it is called spectral decomposition. We are not going into the detail, but this decomposition is called spectral decomposition because it is decomposed via spectra. So as we have stated that in order to orthonormalize the eigenvectors, we need to apply the Gram-Smidth process. So though you must have studied at some stage the Gram-Smidth process, here let us recall the process. This process is for is to obtain the orthonormal set of vectors from the given linearly independent vectors, say v1, v2, v3. So we follow the notations. Whatever the eigenvalues we get here, we call them v1, v2, v3, and after applying the Gram-Smidth process, the resultant vectors which are orthonormal, we call them w1, w2, w3, because most of the times we will be dealing with the eigenvectors of matrix 3 by 3, and then we similarly you can generalize the process for vectors in Rn. So what we will do, we are given the linearly independent set of vectors, say v1, v2, v3. Using these formulas we can find out the vectors u1, u2 and u3. These 3 vectors are mutually orthogonal. So how to get? So u1 is same as v1, u2 is v2 minus inner product u2 with v1 over norm of v1 squared dot product v1. Similarly we get the u3. The vector u3 is the v3 minus projection of u3 on v1 minus projection of u3 on v2, that is v3 minus u3 v1 upon norm of v1 squared into v1 minus u3 v2 inner product upon norm of v2 squared into v2. Similarly you can generalize the things for vectors in Rn, but for our purpose the vectors in R3 we apply these formulas to get the orthogonal set, and then we normalize this u1, u2, u3, that is dividing by its norms. We get the w1, w2 and w3. So these 3 vectors w1, w2 and w3 are orthonormal sets, right? So this is how using applying the Gram-Smidth process we can produce the orthonormal set in Rn. So let us see the example where we want to orthogonally diagonalize the matrix A, that is we want to find out the model matrix P which diagonalize the given matrix A. The given matrix let us say it is A is first row is 4 2 2 2 4 2 and 2 2 4. Observe that this is symmetric matrix. Also remember that the orthogonal diagonalization process is only for symmetric matrices, because we get the orthonormal set of n vectors, n eigenvectors for symmetric matrices. So let us first of all find out the characteristic equation for the matrix A, that is determinant of A minus lambda I. Here it is an printing mistake, that determinant of A minus lambda I is equal to 0, so that we have this determinant 4 minus lambda 2 2 2 4 minus lambda 2 2 2 and 4 minus lambda. Now on expanding you will get the characteristic polynomial, and the factorization of characteristic polynomial is as follows: lambda minus 2 whole squared into lambda minus 8 is equal to 0. Or by the other method also, using the trace determinant method, you can find the characteristic equation for the given matrix. That is not an issue. It is easy to verify that these are the factors of the characteristic equation. Therefore the roots of this characteristic equation are the eigenvalues for the given matrix A. So here eigenvalues are 2 2 and 8. These are the eigenvalues for the given matrix. Now for each of the eigenvalues we will find out the basis for eigenspace. So we want to find out the basis for eigenspace, and for that, for lambda is equal to 2 we find out the basis, and for lambda is equal to 8 we will find out the basis for the eigenvalues. So when you compute the eigenvectors of lambda is equal to 2, we get two linearly independent eigenvectors. v1 is equal to minus 1 1 0 and v2 is equal to minus 1 0 1. Here 2 is repeated 2 times. Therefore we apply Gram-Smidth process on these two vectors v1 and v2 to get the orthonormal eigenvectors corresponding to the eigenvalue lambda is equal to 2. So applying Gram-Smidth process on v1 and v2 we get the orthonormal eigenvectors. So what are our vectors v1 and v2? So we wish to apply the Gram-Smidth process. So here the vector v1 is, given vector v1 is minus 1 1 and 0,